All right, everybody, I'm back. I'm on page 244 at the bottom. I'm going to do question C, and we'll see how long that takes, and maybe do question D. So this time we have two functions, and so there's a couple of interesting things about this. One, there's two functions, right? We're going to rotate the region bounded by these two functions and x equals 3 about the x-axis, and then we're going to use 50, 100, and 1,000 cylinders to approximate the volume that we get. So what's interesting is that there's only three things. There's not four. It feels like there should be like a left bound, a right bound, a top, and a bottom. But also, if you've ever seen someone Vogue, that's like not what they do, but it's pretty close, turns out. So it must be the case that they intersect. So if you look at it, you can tell they intersect at their y-intercepts. So let's sketch this. So, all right, I'm going to put a tick mark at 1. The 3 is like totally arbitrary. Like it could be 10, it could be whatever. It's not like, that's just a boundary that we chose. It's not like given. Well, it's given, but it's not like it needs to be. It's not organic. It's human imposed on this region. Whereas this y-intercept is actually like a feature of the region. So 2x plus 1, I don't know, like that. And then 3x plus 1, maybe like that. Let's do a thing because we're on technology. Let's move this. Oh, crud. Accidental, undo. Okay, I accidentally looped in some of my, oh no. You know, it's like I start out strong and it just, all right, there we go. Okay, and then x equals 3. Say this is x equals 3. So our region is going to be like here. Okay, so we know that they intersect at x equals 0. We know that they don't intersect, but you just stop at x equals 3. So a is equal to 0. So if we were to jot that down, we would say for this problem, a equals 0. And then we would say that b equals 3, because we're going to go from 0 to 3. So there's a couple of ideas for how to deal with this. The easiest one, I think, is to think we're going to find a big volume, and the big volume will come when we rotate the thing that is farther from the axis of revolution. So when we rotate this curve, this is going to give us a big radius, and then we'll get a big volume from that, and then we will get a smaller radius from the inner thing, and we're going to rotate that. And then the total volume of the thing we end up with is the big volume minus the little volume. So that's our plan. Our plan is to do a big volume minus a little volume. And so then it's just a question of like, can we do, what color is that? I think that one. We're going to try to do big volume minus little volume. So to do that, we can just set up our two things, right? So for the big volume, we're going to get delta x. Delta x for both of them actually is going to be the same. It's going to be 3 minus 0 divided by n, so 3 over n in both cases. X sub I is going to be the same for both of them. So x sub I is where you start, which is 0, plus I times delta x, which in this case will be 3i over n. So we want to do this. And then our big volume will be the sum from I equals 1 to n of pi, so don't forget that, the big radius squared. So the big radius comes from not that one, so don't underline that. It comes from this one, the steeper one, right? So we're going to start with g. So g of x sub I, and then I have to square that, and then delta x. So that'll give me the big volume, or an approximation of it. And then what I'm going to do is I'm going to subtract off the smaller volume. So the smaller volume is the sum from I equals 1 to n of pi, because we're always doing pi r squared h. So pi, and then we're using this color, I think. So the smaller radius comes from this function. So it's going to be f of x sub I is the radius, and then we want to square that, right? Pi r squared, and then the height is delta x. Okay, so this is going to work. But look at it, right? They're both the sum from 1 to n. They both have a pi. They both have a delta x. So I could calculate both of them separately, but I could also use some of the properties of summation. So that's what I'm going to do. I'm going to. Also, I should have named this thing. Let me do some iPad magic here. And I'm going to name it the volume as a function of n is equal to this. Okay, so now the volume is a function of n. Anything that doesn't depend upon I can be factored out of these summations. So I'm actually going to kind of do that. I'm going to write this as I equals 1. So I am going to take out the pi. So I'll put that in a different color just so it's like obvious that I did. Pi can come out. Delta x can come out. I'm not going to do that because of calculus-based reasons for later in your life. But you could factor delta x out because it does not depend on I. Let me go back to black. I think that's a good Amy Winehouse album, Back to Black, I think. I think that's the name of it. And then we're going to get g of x sub I squared. So it's big radius squared. And then it'll be minus our little radius squared. And then squared. And then, so you could take delta x out of everything. I'm choosing to take it out of everything, but instead of putting it in front of the summation, I'm going to put it at the end. This is for calculus-based reasons. So later in your life, you'll be like, oh, that's why we did that. Because you're going to do it. So this is what I'm going to use on the calculator. So what I'm going to do is switch over to the calculator, and I'm going to find v of 50, and it'll be an approximation. And then v of 100, which will be approximately something, and then I'll find v of 1000. You got to use every part of the page. You know, when you're complaining about not enough space, did you use every inch of that page? So let's see. Let's switch over. So I'm going to new share. So if you're ever in Zoom, new share, click on the thing you want, and then boom, shows up. All right, let's see. I'm going to define my functions. So f of x colon equals 2x plus 1, g of x colon equals 3x plus 1, enter. All right, so v of n colon equals, so it's going to be pi. So I'm going to type pi, but you should use the key. The sum, you should definitely use the template. I goes from 1 to n of, all right, so big radius is g of, and then x sub I we wrote down was 0 plus I times delta x, which is 3 over n. And then I have to square that. So it's big radius squared minus little radius squared. Say that in your head a lot because that's going to be a thing that is going to come up over and over. And then it's going to be the little radius, which is f of x of I, so plus I times 3 over n. You could do 3i over n, doesn't make a difference, squared. And then inside here, so I've got a little bit of a problem because I need to make sure my delta x is going to multiply by g of x squared and f of x squared. I don't want it just times one of them. So actually, to be really safe, I'm going to put it out here. So I didn't do this on paper, but there's a lot of times that you do something one way on paper and then you do it differently on technology. This is one of those cases where it's just safer. It'll definitely get distributed correctly if we do it this way. So I'm going to do that. So I've got that. All right, let's see. So v of 50, v of 100, and v of 1000. Okay, let's see if the calculator can also find an exact value. So we're going to try to take a limit. Limit n goes to infinity. So I could type infinity, or I can just match this a couple times. Infinity of v of n, 54 pi. That's a nice answer. You could actually work this out. It's a frustum minus a frustum. So that's like a lot of work, but you could calculate it if you were interested in calculating that. So what I'm going to do right now, while it looks like I'm doing nothing, is I'm going to copy these answers down on the notes. 174.481, 172.0, 056. So I'm assuming you're also copying this at this point. 169 point, ooh, I wrote the wrong thing. You'll never know. 169.886. So why do these keep getting smaller, right? So this is one of the things you want to think about. And you probably know the answer, but it's a thing to think about. So these keep getting smaller because, back to the notes, we're making all of our little delta x cuts, and then we're going to use the right endpoint. So if I just make one kind of representative one, I'm going to do it in this weird color. It's like here to here, I'm over counting. I'm always over counting. So as I use more and more, my estimates will get smaller and smaller until ultimately I use an infinite number and I get the exact value, which turned out, I think, to be 54 pi. But until you do that, you're always going to be over in this particular case. Increasing, decreasing functions will change whether or not you're over or under. To see why that is, draw, just in the first quadrant, draw y equals 5 minus x. And then draw your rectangles that you're going to rotate, right? So you start at 0 and you go like delta x and you go up to the height and draw your rectangles, right? Doing this. Actually, I could just do it. I don't know why I'm like pantomiming this whole thing. I'm gonna like blow this way up and do it here. So, right, 5, 5. So this is 5 minus x. And then just do 1. Look at that. You're under counting. So if we do this and we increase the number of rectangles that we use that become cylinders when we rotate, we're always going to get bigger and bigger answers. And that's because this is decreasing. If a function is increasing and decreasing, all bets are off. Sometimes you're over, sometimes you're under. It could magically work out that you get exactly the answer. Seems extremely unlikely, but it could happen. So that's kind of a lot to absorb. So it's when you have two functions bounding your region, you're going to get a big radius and then a smaller radius. And what you do is basically find the big volume, find the small volume, and subtract. But you can conveniently combine them, which is what we did here. We conveniently went from this to this because it's really messy to do the first one. It's a lot nicer to do the second one. So I'm going to stop this here, come back, finish this page, and then who knows, maybe move on. But I hope you found this helpful.